What's up, my chemistry students? This is Thompson here, and today we are on a new unit. We're working on thermochemistry. This is an introduction to thermochem. Here in this picture, you see my favorite Muppet. It's Beaker, and he's playing with fire. Dangerous. All right, so we need to know what thermochemistry is. So that root here, thermo. Thermo means heat. Okay, so thermochemistry is the study of heat, but it's the study of heat involved in chemical reactions. And it says here it's the study of energies, because we're talking about heat energy in chemical reactions. Here is a video called Eureka, and it talks about how temperature is measured. Love this video.
Can you tell whether something is hot or cold? In that case, decide which of these 3 bathtubs you'd like to step into. This one, which is freezing cold, or this one, which is boiling hot, or this one, which is neither too hot nor too cold. It's an easy choice, isn't it? Well, go on. Step into the middle one. Feels just a bit too hot, doesn't it? Try the other foot. Oh, now it feels a bit too cold. Well, perhaps judging whether something is hot or cold isn't so easy after all. This is because the human body can only notice differences in hotness or coldness, how hot or cold something is in comparison with something else. But even your own feet can't agree about how hot or cold the water in the middle bathtub is. There must be a better way to measure degree of hotness, or temperature as we usually say. What do we know about hotness? Well, when the temperature of something goes up, its molecules go faster. The molecules in the boiling hot bath water are going too fast for comfort. And the molecules in the freezing cold bath water are going too slowly for comfort. If we could only make sure that the molecules in the in-between bath water were going at just the right speed for the human body, you could take your bath. But how can we measure their speed? Molecules are so tiny, we can't even see them, let alone clock how fast they're going. Wait a minute. There's something else we know about hotness. It not only causes a speed up of molecules, but this speed up causes matter to expand. So we could measure molecule speed indirectly by measuring the effect of that speed, the expansion itself. And that's exactly what a Swedish scientist by the name of Anders Celsius did in 1742. He took a liquid that expands quite a bit when it gets hot, mercury, and poured it into a little tube. He then put the tube into some freezing cold water, and the mercury contracted down to here. He decided to label this freezing point of water 0 degrees Celsius. Next, he put the tube into some boiling hot water, and the mercury expanded up to here. He marked this boiling point of water 100 degrees Celsius. Now he had a means of measuring the relative speeds of molecules. In other words, the relative temperature or degree of hotness of things. Comfortable room temperature is 20 degrees. But 30 degrees is a bit too hot. And minus 20 degrees is much too cold. Celsius could even take his own temperature and find it to be about 37 degrees, which, naturally enough, is the ideal temperature for your bath water, normal body temperature. All you have to do is adjust the water to 37 degrees, and you'll finally be able to take your bath, courtesy Anders Celsius and his hotness meter. Or if you prefer the Greek word for hotness, which is thermos, as in thermos bottle, his thermos meter, or thermometer. Is your bath water at the right temperature now? Oh my. Perhaps you should have taken a shower.
Couple things you had to get there. One was how temperature is a measure of the speed of the molecules. Another is the freezing point of water and the boiling point of water. So freezing point of water, 0 degrees Celsius. The boiling point of water, 100 degrees Celsius, something we'll use throughout this unit. And that's at standard pressure, though. All right, so we need to know the difference between heat and temperature. Okay, so here we go. It says heat measures the total amount of kinetic energy in that substance, whereas temperature is measuring the average kinetic energy in a substance. So it's how fast those particles are moving, not the total amount of movement, but just how fast they're moving. The unit we measure heat in is a joule or a calorie, and we measure temperature in degrees Celsius, degrees Fahrenheit, or even Kelvin. The instrument that we use to measure heat is called a calorimeter or calorimeter, and the instrument we use to measure temperature is a thermometer or a hotness meter. And then the last thing we need to know about heat versus temperature is heat actually depends on how much of that substance you have, whereas temperature does not depend on how much you have. And I'm going to show you this next video, and it clearly illustrates how it really depends on how much you have for heat and not for temperature. It is another Eureka video.
Temperature versus heat. Here's a bucket of hot water at 50 degrees Celsius. And here's a cup of freshly boiled water at 100 degrees Celsius. In which of these two containers are the water molecules moving faster? The bucket or the cup? That's right, because the degree of hotness of the water in the cup is much higher than the degree of hotness of the water in the bucket. And the hotter something is, the faster its molecules move. Would you say, therefore, that there's more hotness in the cup than in the bucket? In that case, if the water in your swimming pool is just a bit too cold for you, you'd be better off emptying the cup full of boiling water into it, rather than the bucket full of water at the lower temperature, wouldn't you? Or would you? You don't seem so sure. Let's do an experiment to find out. Suppose you had two identical swimming pools, one yellow and one blue. And suppose that the water in both of them was just a bit too cold for you. When you pour the cup of boiling water into the yellow pool, does the water feel any warmer? You can hardly feel any difference at all, can you? Now pour the bucketful of 50-degree water into the blue pool. How does that feel? Quite a bit warmer? Aha! So even though the water in the cup was considerably hotter than the water in the bucket, the 50-degree bucket water is much better at heating up swimming pools than the 100-degree cup water. Why is this? Well, let's look at the facts. The bucket obviously contains many, many more water molecules than the cup does. The temperature of the average molecule in the bucket is 50 degrees, and the temperature of the average molecule in the cup is 100 degrees. Now let's substitute something else for the molecules. Imagine that instead of molecules, the cup were filled with $100 bills, and the bucket with $50 bills. Which would you rather have? Each individual bill in the cup is worth much more than each individual bill in the bucket. But the total amount of money in the bucket is much greater than the total amount of money in the cup. It's the same with hotness. The degree of hotness, like the value of the dollar bills, is higher in the cup. But the quantity of hotness, like the quantity of dollar bills, is greater in the bucket. We know that it's the speed of the molecules that determines the degree of hotness of something. In fact, degree of hotness only depends on speed. It has nothing to do with how many molecules there are. Although the molecules in the bucket aren't going as fast as in the cup, there are more of them, so they more than make up in mass what they lack in speed. And it's mass, combined with speed, that determines quantity of hotness. We've already seen that the word for degree of hotness is temperature. Now it's time to introduce the other word for quantity of hotness, which is heat. The big difference between temperature and heat is that temperature depends on speed only, whereas heat depends on both mass and speed. The water in the cup has got a high temperature, but very little heat. And the water in the bucket has got a much lower temperature, but a great deal of heat. Now you know why buckets of 50-degree water are better at heating up swimming pools than cups of boiling water. On the other hand, if you're looking for somewhere to dunk your tea bag.
Okay, next we're going to talk about heat flow. If you've ever had the door open in the summertime and your dad gets mad at you and says, "Hey, shut that door. You're letting all the cold air out." He was saying that incorrectly because heat doesn't flow that way. Heat always flows from hot to cold. And so when you leave the door open in the summertime, you're letting the warm air in, not the cold air out. Same thing for a refrigerator. So you see this picture of a refrigerator right here. The way a refrigerator works is it removes heat. So there's these little coils in the back. There's the picture there of the red coils. If you've ever felt the back of a refrigerator, it's very warm. The reason for that is the heat's coming from your food into those coils, and then the coils release the energy into the atmosphere. So it feels warm around your fridge. It doesn't add cold, it just simply removes heat. Okay. All right, next we're going to talk about energy. And energy is the capacity to do work or supply heat. Okay. Do work, move something, or produce some heat to change it, cook it, maybe, possibly. All right, there are different forms of energy. You don't have to know every single one of these because we're only interested in the ones that apply towards chemistry. So the two main forms of energy here are kinetic energy and potential energy, and then there's all those different ones underneath those main headings. Here we go. So again, first, the two forms of energy that we're concerned with are kinetic energy, we call Ke for short, and potential energy, Pe for short. Kinetic energy is the energy that an object has because of its movement. We learned this when we were talking about the kinetic molecular theory. Potential energy is stored energy. Okay, heat is just an example of thermal energy, and thermal energy is a type of kinetic energy. Remember that heat is the total amount of movement or kinetic energy that a substance has. Okay, we need to know that bonds can store chemical energy, and since stored, we call that potential energy. So things like food store chemical energy, they still store potential energy, and you take advantage of that energy by eating it. So when you eat the food, you break the bonds that are in those molecules like glucose, and you release the energy that's trapped within it. In order to make those bonds, energy had to be added. So glucose is produced by plants, and it requires sunlight, it requires energy in order to form those bonds. So that means that we can change energy. Energy can be changed from one form to another. And so here you see some examples. Light energy goes into chemical energy as a carrot grows. Electrical energy can go into a stovetop and turn into heat energy. Chemical energy stored in an ice cream cone can go to mechanical energy as you ride your bike, and chemical energy stored in gasoline can go towards mechanical energy as you drive your car. And this transformation of energy is summed up in the law of conservation of energy. It states that energy is not created or destroyed, it's simply transformed. And so it goes from one form of energy to another, but it's kind of cycled through. This is actually the first law of thermodynamics. Last thing we need to know are the units of energy. And so we have joules, calories, little c calories, and big C calories. And that makes a difference between the size of the C here because they differ in a factor of 1,000. All right, the big C calories are food calories. So when you think of those, think of nutrition facts. Think of the big C calories that are on the back of, let's say, your juice bottle. Here are the conversions, and you do get these on the back of your periodic table. 1 calorie is 4.184 joules. 1 big C calorie is 1,000 little c calories. And so anytime you eat a calorie, like a food calorie, you're eating 1,000 little calories. You need to know that 1 kilojoule is 1,000 joules. And another conversion we might use is 1 kilocal is 1,000 calories, or 1 kilocal is 1 big C cal. All right, so let's try one. Convert 8.5 joules to calories. We're just going to use the conversion factors we need. So I've got 8.5 joules. I want to cancel joules, and the only thing that has joules in it that can cancel it, actually we have two. We have this one and we have this one. I don't want kilojoules, so I want calories. So I'm going to go ahead and go to this one. So I will multiply by the 4.184 on the bottom, since I want that to cancel, and the little c calorie on top. Joules cancels, and I get 2.0 calories. I'm just rounding to the same number of significant figures as the given. Okay. Second example, convert 4.50 kilojoules to calories. These are little c calories. In 1 kilojoule, there are 1,000 joules, and so that would go on the bottom, 1 kilojoule. Since I want kilojoules to cancel, 1,000 joules on the top, kilojoules cancel, and I'm still not done. I need to change it to little c calories, so I have the conversion. 1 calorie is 4.184 joules. So we want joules to cancel, so the 4.184 goes on the bottom. And we get 1,075.52 calories, which we need to round to 3 significant figures, and so that's 1,080 calories. Okay, hopefully that was a nice, simple, easy start to thermochemistry.